laptop is just dying straight up.
I imagine.
Is the stream up?
I don't know. I don't have Twitch open.
Let me open it up on my phone because my laptop's taking way too long to open it up. It's up on YouTube.
But yeah, we're live.
I think it's up on YouTube. Yeah, we're live. Alright, that's good. We'll wait like 5-10
That's so
more
exciting.
minutes for everybody to join.
Yeah, we're on my work VM. I have a lot of, or like my work computer, I have like a lot of VMs running. So the fan is just constantly going.
Yeah. That's like my computer at home. I just always have it on. Turn off at night, but that's pretty much it. And then my workplace, like our lab, we just have, I don't even know how many computers. There's probably like 200, 300 computers in that building, in that lab. It's just one lab. And last week they had an issue with heating. Like I was in there working. Maybe I was in there for like, I think 30 minutes max. I was in there and I was just dying from heat.
Yeah,
and like
I know
we
that
work,
feeling.
yeah. And I work with SSDs too, so I have to have like this heavy lab coat on so that I don't like, I don't like generate static or anything. I usually take it off, but then this one time I had it off and one of the coworkers just came and he's like, "You're working with SSDs. Put your lab coat on." And I was like, "Man, it's so heavy and it's like it just boils you."
That's awful. I was gonna swear that we are live, and I probably shouldn't swear on broadcast.
Okay. I think I don't even know how many viewers we got. Oh, he actually tells us people are in. Okay, I think should be good to start. Let me just double check on my phone because my laptop's dying. Where is Twitch? Oh yeah, we got 11 people. We're good. Okay.
Beauty.
Hello everyone, and welcome to our Docker and Container Workshop hosted by Ryan Prairie. Ryan, you may take over now. If anybody has any questions, I think Ryan will tell you if he wants them now or later.
You can just throw it in chat. If it's a big question, I'll probably save it till later. If it's a not as big question, I'll probably answer it. Yeah, so Docker and containers. Whales. So let's start off with what is Docker? So you might have heard of Docker or containers or a whole bunch of stuff, and they're all related. But the community has a really bad, very bad time at naming things. And so almost everything's called Docker. So really, Docker is a series of applications that let you create reproducible, isolated, easy to use bundles of files and stuff, and those are called containers. You can run containers, you can download containers, you can do a whole bunch of stuff. So there's thousands of pieces of software named Docker. Not actually, there's just a lot. These are just some examples, Docker Desktop, Docker Runtime Shim, Docker CLI, Docker Compose, Docker Swarm, whatever. So it is important to understand that containers are an isolated environment, that they stand completely alone compared to the rest of the system. That's important because it lets you create reproducible packages of applications that work on all kinds of systems because they're all isolated away from the system. And so because Docker is isolated, it has no privileges by default. You need to grant the privileges to the containers that are made. So Docker also has images that you build. These images are actually used to create containers. And images are just like a snapshot. We'll cover more on it later, but it's like a snapshot of what the container should be like when it starts up. You create an image by making a blueprint file. That blueprint file is called Dockerfile. So if you really think about it, it goes Dockerfile, image, then a container. All right, perfect. All right, this is another little infographic. on it. So containers versus virtual machines. You might be thinking like, how are containers different from virtual machines? And that's actually a very good question. Virtual machines, by design, create a mostly reproducible environment. They are isolated because they're a whole operating system running on fake hardware. Then they are managed and controlled as well by a hypervisor. But there are some big differences. Virtual machines run a whole operating system, not just the application, but the whole operating system. They're managed by a hypervisor. A hypervisor is like a big overseeing application that oversees, virtual machine creation and management. They're they're normally very chunky. They're very big, very large. Um, what about containers now? Well, containers, they share the kernel with their host operating system, which means that on top of the container is just a series of user space applications. It really shares the kernel and the actual heart of the operating system with its host machine itself. So one big thing that really made it click to me of what containers are away from virtual machines are operating systems are essentially just one big configuration around a kernel. They have some applications, they have some files, and some other stuff. But at the end of the day, it's all just stuff around kernel space. And so when you want to reproduce, an operating system or what feels like an operating system to an application, you really only need to recreate user space. And because of the shared kernel, the kernel is just the same. And so because the shared kernel, containers are much, much lighter weight. They're very useful when you only need the application. But if you need like a whole operating system, let's say you're running like a VPS, a virtual private server, you need to have the whole operating system for the user to interact with. That's what virtual machines are good for. But containers are not virtual machines. They're different. So now that we know what a container kind of is, and we know that they come from images, what are images? Images are a snapshot of what the container should be like at the beginning. You create them by making Docker files and building them. To make caching of images a lot easier, images are built on top of layers. In a Docker file, you have multiple commands, and per every command that you make, a new layer is added. Each of those layers are actually images themselves. And so if you want to make just a single layer, or you change like a big part of your code, but that happens later in your Docker file, the beginning stages will be cached for you. And so that's very useful. Images can be tagged and versioned, which means you can be like, oh, this image is for this version of the software, whereas this image is for not. It's for a different version of the software. And because of that, they can be uploaded to registries, called container or image registries. And from there, people can just download them on the specific version. That's really important, and essentially lets you create your code one place, upload it to somewhere, anyone can download, and then they have a ready-made application to use when they download it. So there's a ton of different types of images, Scratch, distrless, Docker and Docker. They're all images or containers, but they all do different purposes. Scratch images are created when there's no user space. It's just empty. There's nothing in there. It's just completely blank. And so that's really useful if you have like a single binary that you want to execute. Let's say you have like a Go program or a Rust or a C program. Then you want to execute it inside a container. You just package it up into a single executable, and you put it in that container. There's only there, and that's it. And if you need a static binary, then Scratch containers are really good. It really lowers the amount of CVEs that can happen, of exploitability that can happen to these machines, because there's only a single program in there. Single program, that's it. Now, distrless containers are a little more complicated. If you think of like Ubuntu images and Ubuntu containers, they have like a large part of the Ubuntu, stuff. Like it has, files, it has curl, it has wget, it has whatever. But if you just want to run a Python program, you don't care if there's like 1,000 other programs in there that you might not need. So distrless containers was an idea made by Google to get around. It just has the program runtime. That's it. It is the bare minimum you need to get a program up and running in a specific language. They have distrless containers for Java, They have distro list containers for Python, for Node.js. There's a whole bunch of them. So those two are very popular, especially in the security container world. Now the last one, DID, which is Docker and Docker, it is just as it sounds. You're running Docker inside a Docker container. And so you can have containers that are essentially like Inception. Like you got to go deeper. You're like a container wrapped in a container wrapped in a container. It is generally frowned upon, but on some systems it's actually necessary to do Docker at Docker. Yeah, so that's a brief overview of images. Now Docker files. Now, we actually covered a bit on images and Docker and containers, but what about Docker files? How do you actually make them? The Docker files are actually really important. They're the blueprints for images. If images define the initial state of a container, Docker files go through all the steps to get you to an image. So they define all the steps that should be taken at build time, and then the first initial step at runtime. So Docker files. So would you be showing all these actions? Yes, I will. I'll be showing a whole bunch of them. I have a 3 demos at the end to show. So we can have multiple stages. So in a Docker file, your Docker file has to start with the from that is building off another image. So if you want to build off of the Ubuntu image, you want to put your program in essentially an Ubuntu container, you would write like from Ubuntu and then the version. If you want to run like 21.04, you can totally do that. So you use your starting image, your from command at the beginning, and then you build on top of that. If you need to run things at build time, let's say you need to install a program, you would use run. This could run any like shell program, whether your container runs bash or whether it runs like PowerShell. Yeah, run is a very important command. CMD is also a very important command, but it does it at runtime. If you need to run a command, one command at runtime, you would use CMD. So let's say, you put your application in a container, but you want to start it up. You would use CMD to do that. You would call it. Now, but how do you get things inside your image? So you would use copy for that. Copy just takes files from outside your image and puts them inside your image. It's not very complicated. There is another function called add. Don't use add. Add is deprecated and not recommended by Docker. The big reason why is that add also lets you pull in from URLs and like remote hosts, and so it can get complicated of what it is actually doing because it can do a whole bunch of things at once. Yeah. So then we move on. Let's move on to user. User is very important. So user sets the UID or the GID of the user in the image and on the container. So if you want to, by default, on a lot of images or containers, you're a root. Let's say you don't want to be root. You would use the user command to change yourself to a new user. Yeah, now workdir, it's cut off a little bit in the stream, but basically it changes the directory you're working on. Every container and image has a default directory to work on, but if you want to, instead of writing like copy like this application into this spot and then also this path at the end, that's just a huge hassle. Workdir is a way to get around that. It also makes a default entry point for when you need to attach to a container. I'll be covering on that later. So last two, arg and env. Arg is for making build time variables that you specify when you're actually building the Docker file into an image. And then env creates runtime variables that are used in the environment during running the actual container from an image. So now that we got a little bit of a 3,000-foot view, we got to think about multiple stage builds. So let's say you copy your entire program, whatever it is, into your first stage. It could be Ubuntu, it could be whatever. And your let's say you have like a C program. and you want to, run it in a very safe and secure environment. Remember Scratch earlier? Scratch is a perfect example of an easy and secure environment. But it's not a good idea to copy over all of your code, the entire build system, into a Scratch environment, because then you just cluttered your Scratch environment. And so a way to get around this is multi-stage build. So you grab your code, you put it in one stage, let's say Ubuntu or wherever, and then you build your code. And then from there, you can copy, you make a new stage. And then in your new stage, you copy from an old stage. And then it just pulls the code into the new stage. And then that new stage is the entire thing. This is really useful, because, as I said before, when you want to have very small, minimal containers just of your application. It can be used in tons of other ways too. All right, so that's a little review. Now, we know what Docker is. We know what containers are, kinda. We know how images kind of work, and we know how Docker files kind of work. But how do they actually work? Who made these decisions? Was it Docker? Well, kind of. The big thing comes from OCI. OCI is the Open Container Initiative. It was, well, I'm not 100% sure, but I've read that it was a way for Docker to both standardize the industry and corner the market. So back then, there was a whole bunch of different kinds of containers and runtimes, a whole bunch of stuff like that. And Docker was one of the big ones. And Docker teamed up with Google and Microsoft and all the big companies, and they standardized and they became OCI. Now, OCI and Docker are separate groups, but most of the people that work at Docker also work on OCI to create the standard for the industry. So OCI containers are actually like ultra lightweight, ultra flexible, and they're not just limited to Linux like we would think about. There's multiple kinds of OCI containers, but the general idea supports all of them. Now, OCI containers can work in tons of different environments. There's Linux, of course. There's ones for Solaris, which is a very old operating system. There's one for Windows. You might have heard of Docker Desktop for Windows, or WSL, which is based off of containerization. So those are big, but there's also virtual machine OCI container. So those are OCI containers that deploy on virtual machines. I once read an article where Nginx talked about how they, on like a big cloud platform, they use like a special runtime to deploy VMs like that through Kubernetes. My team at NVIDIA does a very similar thing where we deploy what is essentially OCI VMs through an OCI VM runtime on Kubernetes. And so this way you can create virtual machines that are reproducible and easy to use, but can pop up everywhere. So OCI containers are essentially just an interface, and Docker implements that interface, and then the step in between the runtime that you want, whether that's Linux containers or Windows containers or virtual machine containers or whatever, that space in between is called a Docker shim or a runtime shim. Now, runtime shims are extremely important. They're used all over the place. Every containerization program has a runtime shim in it, and it does a lot of very important things. Now, the runtime shim, as I mentioned before, it's important, so I'm going to repeat it, is the step in between Docker and the container runtime. And so Docker really can work on all kinds of OCI containers as long as it has a runtime shim to run them. All right. Now, whales. Whales, whales, whales. Whales, whales, whales. So yeah, that's the end of the presentation, but now let's do some demos. All right. So here I have Emacs. And here I have a terminal. All right. So I have 3 demos. I guess I can do a fourth one on attaching 2 containers. So yeah, let's go over it. So I have 3 that we care about. Let's start with the easiest one, called single. It's called single because it has one stage. So the one stage is very simple. It starts off, or I guess I should introduce my program too. So this is in Go because it is a small, easy programming language that I know and like, and also works very nicely in it creates binaries. So that's very good for our purposes. So you can see here, I'm just printing out hello from a container. So now let's look at the Dockerfile for this. The Dockerfile is fairly simple. We start off from the base image of Go, or the Golang image, and there is a version 1.18. And then I copy everything in my in my current directory, which is these three files here. And then I put it in my current working directory. My current working directory, because we did workdir, is /app. And then we run go build to build it into a single binary. And then we run that binary. So remember earlier, all of these commands work at build time. Only the last command, cmd, works at runtime. I realized I forgot to mention Docker Hub. So if you're like, where are these containers coming from? Where are you pulling them from? Are they magic? That's a good question. Hub.docker.com is Docker Hub. You can search up anything. You can search up, like, it says here MySQL. So let's search it up. MySQL here. We have a bunch of different ones. If it says Docker official image, which means they worked with MySQL, and they created this image. Oh, I see a question. So the run is like compiling a C file and CMD is running it. Perfect. That is a very good analogy. Run isn't actually just for building. It could be doing anything. I could do run, touch, and then, I don't know, like hello. And this would make a file called hello. I could do anything. Do like echo hi there or whatever. And it would run that at build time. And so CMD is actually running the container. It's running the thing in here. It uses a special format called array format, something like that, where your arguments need to be in this array like syntax. So Docker Hub is important, and run and CMD do similar things, but at different times of the application lifetime. So now that we have this and we know what my program does, let's build it. All right. I'm here. So we go to single. That's where it was. I mistyped it. Thank you, ZSH. So let's do Docker build. No, the build. -T for tag. It's like a label or a name. You can name it whatever you want. If you don't, then it gives you the name of it's like the hash of the Docker image and like a whole bunch. It's complicated, and I don't know completely, but okay. So Docker build, and then we can call it whatever. Let's do single, and then dot for our current working directory. So we run this, and it's running. Perfect. So we can see the steps. These are the layers. So from Golang 1.18, that is the hash or the short of the hash of the Golang 1.18 image. So the first layer, it's like, oh, this is the hash of the first layer. Okay? And then this one was currently my cache. So it says using the cached version. And then similar thing here, copy everything from outside, inside, then run go build. And removing intermediate container, I guess it just figured that it wasn't needed. Running hi there, and we can see right there, hi there. Now removed another intermediate container. And then this is the last step. It's not actually running. So if we want to run, we would do Docker run, and then the name of the image, which is single, and then it's tagged with latest. By default, it is tagged with latest. It is not always best practice to tag things with latest or to use things tagged with latest. That is because if they actually change the version and your code needs version-specific software, then it'll brick. If I need like Postgres version 2 when I pull from latest and they just updated latest to be Postgres version 3, it's going to break. You're going to have a bad time. All right, so let's run this container. All right, it was pretty short. It just printed to standard out. That's not particularly exciting, that one, but it was a very simple experiment. So let's move on. So I have this one multi. It is, let me close these buffers. Multi says here, hello from a container, but like again, So pretty much the same thing, but we're doing it differently this time. So now we're using a multi-stage build. You can see it here. So from Golang 1.18, and then we call this stage builder, builder right there. And then here, we, just like before, we make the app, we copy all the files in, and then we actually run the building program, go build. And then we make a new stage from scratch. Scratch, remember before, nothing in user space, completely nothing, straight up empty. And then we copy from the builder our application, multi, because that's what it was called. It was built as multi. And then we copy that into app. And then we copy it as app. That's its like new name. And then we just run it. So if we go up and then we go over to multi, and then we run docker build again, -t for multi, and then done. And I mean, it's all cached because I ran it last night, but I can show you how it breaks cache. I added this new command very early on, because layers, they build upon each other. If you change something early on, it's gonna, be broken. And so if we run this now, only the first two stages were cached. Every other stage had to run, from new. So that actually leads me to a good topic. When to think about lifetimes. So if we go to my GitHub, I can show you something that I was working on and a mistake that I made. It's uwindsor CSS. So I was working on the bot, and I was working on the Dockerfile for the bot. So I used to do, it's very big because there's a lot of stuff that needs to be installed. But here, this installing dependencies part. I didn't used to do this. I used to do this part after I copied everything in. That was a mistake. It was a huge issue because every time it had to build all the dependencies, it could take, I had to compile some C code and do like a bunch of stuff. And it could take, 4 or 5 minutes. And that was like a monster pain. And if you did it after you copied in all the code, if the code changed for any reason, if you modified the code, but not the dependencies, then you need to rebuild the dependencies every time. That was awful. Straight up, it sucked. And so you get around that. Here, I copy only in the dependency files. For Ruby, it's gemfile and gemfile.lock. And then I build the dependencies themselves. And then I copy the files. This way, these stages will be cached, while this stage, isn't. And that's just an example of a mistake that I made and how I fixed it. All right, yeah, copy dependencies first. That is a good takeaway from this. Let me just have some water. All right. All right. So now that we've seen these two demos, now I actually have a fancier demo. This one is just a web server. By the way, bad practice. Don't actually write Go code like this. Monkey patching is bad. But it's short and I don't care that much. So here, it's basically the same thing as the single one, except it has a new command, this expose command. Also, for some reason, I tagged it builder. That was a mistake, but doesn't matter. Yeah, expose. So expose is a directive or command or whatever you want to put, but it doesn't actually do anything. It's just documentation for the user. So when how Docker containers are isolated, you need to give them privileges. If they want to create ports, they can create ports inside the container, but they don't talk to the outside world. They're not actually published to the full computer's like routing list. There's no ports exposed to the whole wider computer from inside Docker. So you need to actually publish them yourselves. So the expose directory, or not a directory, the expose command tells whoever is running your image that it actually puts forth these these ports, and so you need to deal with that yourself. You know, and so here I'm exposing port 80, and it's over TCP. All right. Now let's go over to server, and yep, we got build dash e, and then we'll call it server. Through pres, just because I might already have an image called server that I made a mistake. All right, now let's build it. All right, that was fairly quick. So now let's run it. Run runs latest. So you see here is hanging. If we go to the browser and we go to localhost, it's 80. There's nothing there. Because we didn't publish any ports. It's just internal. Right? So let's publish the ports. I believe it's -p, and then the port we want to publish, or no, the user space port, and then the container port. So 8080 just because it's easy, and then 80. Now if we reload, oh, that was fun. Oh, because I'm on the wrong port. Whoops. All right, thank you, Firefox. Let's get rid of the HTTPS, and yeah, we can see here, hello from a container, but like a third time. Make it bigger, and so exciting. Yeah, that's pretty much it. But I want to show you one last thing. So we have done all of this, but what if you want to interact with the container in, actually, it's called attaching. So we would do that. So we would do Docker run, and then let's do like Ubuntu. I don't know, like 21.04. That's just a version. So yeah, so we run this. Whoops, I might not know the syntax. That'd be very funny. All right, so now it's pulling the image. So now we have it. And now if we run it, it would do nothing. There's nothing for it to do. There's no command that's being run. It's just like Ubuntu, it exists, and then it stops because it doesn't run anything. But if we want to attach to it, I believe it is --it/bin bash. Oh, I might have this wrong. That like this. There we are. Okay. So IT. So these are actually two like flags. So I is interactive, and I believe T is attach. Um, so they do two very similar things, and they work together. So attaching means the container has std in, std out, std error, and when you want to attach to them, you're literally grabbing. I mean, not literally. You're figuratively taking the streams from your shell, and you're just attaching them into the one in the container, and so it literally just passes it on. Um, this is a very useful thing, and I once made a program where I was like connecting to streams, and this works not just for SCD and SCD out, it works for all streams. So if you want to attach any stream to this, it can attach. So I made an application that puts you in a container from an SSH server. So in that container, or in that program, the big thing that I did was I attached the input stream from SSH, put it into SDDN, and took the output stream and put it outwards through SSH. And so now we're in the container. We can see that here, and we can just it's just a bash shell. We can do whatever. We could literally nuke the system, and it would be fine. I could do like rm /star blah, 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 and it would work. And then I would just exit out of the container, and I would be fine. But there's no need. Um, yeah, that's pretty much it. If you guys want, I can talk a little bit more about how Linux containers work. But yeah. Yeah, if you guys have any questions or anything, feel free to ask. All right. Yeah, someone asked me a question yesterday. Thank you, Austin. Yeah, somebody asked me a question yesterday. How can I pull and use a container of Ubuntu when like the Ubuntu base image is like 2 gigs? And that was a very good question. Actually, that was a very, very good. That's because like there's not a ton going on. There's no user space, there's no kernel space in the container. Um, and a lot of it is cached because it works off prior stages, and it interacts with smaller stuff. Docker Compose. Yeah, so that's a good question. So um, now that we know what containers are, what is Kubernetes? How does all of this work? It's all magic. And it is totally magic. The people who make Kubernetes are like unbelievable geniuses, and they do amazing work, and it is truly amazing. But Docker Compose is another very similar tool. So these tools are useful for container orchestration. So that means, just like a conductor, orchestrates an orchestra, it is putting together and making sure all the pieces work together. So with containers, the network is by default isolated. So it's very difficult to get them networked together. Sometimes it can be a little weird. Sometimes, and so Kubernetes and by extension Docker Compose, which are both container orchestration softwares, make it really easy for you to just slot the pieces together. For example, Docker Compose has one big file. I think it is literally called dockercompose.yaml. And you just define the containers that you want to run. Sometimes you define where the Docker files are, but more times than not, you just define where the images exist, from the registry or their names. And then it pulls them all, and then it configures them. It can, do actions on this image and create a whole new image for it to run, or it can just network them together so they all talk to each other. A whole bunch of stuff like that. Docker Compose is really useful. So before Docker Compose, I think before Kubernetes too, there was a software called Docker Swarm. Don't use it; it's deprecated. But it was really interesting at the time because it was like the first. It might not have been the first, but I think it was one of the big players in early container orchestration. So you could like hook it up with the database and you could do all that stuff. Docker Swarm was like a really big, influential one very early. Oh, one more thing. Docker isn't the only player in this scene. There's a whole ton of them. Outside of just Docker, another big one is called Podman, which is made by Red Hat. Podman even actually uses its own better, in my opinion, runtime instead of the default one on Docker, which I believe is run C. The C in there is container, not just not the C language, and it's actually written in Go. So Podman made their own. It's called C Run. They're not very good at naming things, and it's actually written in C, and it is faster, and a lot of people like it better. And so it's the default on Podman. All right, I'm not gonna lie, Chris, go for 55. I have no idea what you're asking in chat. Yeah, yeah. I can talk a little bit more about Linux OCI containers because they're actually pretty cool. Linux OCI containers use the two big ones. There's like 4 or 5 different technologies under the hood. But the two big technologies are called namespaces and C groups. You know, on top of just being able to create isolated containers in Docker, you can actually set resource limits. I only want this to use this much RAM. I only want this to use this much. And so, um, you know, one of the ways that it does that is through C groups. C groups is like just a file that you can, or a series of files that you can create in the kernel space, and you just make the files, and then it puts limits on the process that is attached to those files. So for Docker, it makes a process, and it makes the C group based on your configuration, and then it does some kernel magic and puts them together. Now, namespaces is how it does all the isolation. There's 5 big types of namespaces. I don't remember them all off my head, but I think there's a process namespace, a network namespace, file system namespace. That's not important. But the important part is that it provides isolation. They don't, using namespaces, your programs and processes cannot interact with each other in the specified namespace. So if you use a networking namespace, it creates a whole new network stack for your program. Um, Docker by default uses the majority of the namespaces, but it also means that you can configure it not to use any namespace. If you want to use your host networking, your like host operating system's network stack, you can do that really easily in Docker. I believe it is just Docker dash dash network equals and then two double brackets and host in the middle or double quotes. And there's a whole bunch of stuff like that. And it really gets useful because you can share part of the system while still having layers of isolation and security. I used to, I made a ransomware application, and in the application, I was doing a lot of by nature of it, I was just nuking the computer. I didn't want to install into VM and every time, and that was just like a monster hassle. So I actually used Docker to do that. And I created a container for me, and then I just put my program in that container, and I just let my program nuke the container, and then I would just exit out of the container. It was always fine. And that leads me to another really cool software called Earthly, earthly.dev. And Earthly is a CI/CD framework that runs in containers and does a lot of magic. It's like Makefile meets Docker. That's how I like to put it. It has the syntax. Personally, I don't like it, but it's very Makefile, and it works on stages. So I have like a ton of projects that I have made Earthly files for. But here's a fairly complicated one. This was the ransomware bot. And you can see here in my Earthly file, there's like a whole bunch of different stages. So it has the base stage, which just gathers all the dependencies, downloads them all, and then this actually builds the client. So it works from the dependency stage, copies the main Go file in here, copies a bunch of directories too, and then it runs build, and then that's it. It just builds the software, and then Earthly can actually save artifacts inside and outside the container. So if you need your file to be pulled out of the container, artifacting on Earthly is the best way to do it, in my opinion. It's actually how I translated my a build thing that I had from inside a container, which was a series of like 6 or 7 different shell scripts, and it's complicated coding mess, to just single file, and it worked just as well, if not better, in my opinion. So that's pretty much it. I can You guys got any questions? All
I
right, I'm
think
assuming
that's
no.
good. Yeah. Thank you
Yeah,
so much,
thanks.
Ryan, and thank everyone for joining.
Thank you for
And
joining.
have a great day, everyone.
Yeah, thank you. Bye bye.